Scientific cosmology is about a century old. Of course, the ancient Greeks speculated about the size, shape, and nature of the universe, but these pre-scientific ideas were based on speculation and logic. There were no ways for them to measure things and decide between different theories, although they had some strikingly modern ideas, even working without telescopes. Then, in the Copernican revolution, the Earth is displaced from the center of the universe, and that's a progression that has continued for the centuries since Copernicus. Galileo's use of the telescope showed that the stars are likely to be distributed in three-dimensional space to vast distances, although he could not measure their distances. The first stellar parallax was not measured until 1838. By late in the 19th century, William Herschel was using larger and larger homemade telescopes to map out the Milky Way, using the relative brightness of stars to guess at the distances and the sizes of our galaxy. But even that issue was not resolved till well into the 20th century. Harlow Shapley, out of the Harvard College Observatory, made the critical observations to show the size of our galaxy. Modern cosmology really starts with Edwin Hubble and his twin discoveries of the extragalactic nature of the nebulae, that we live in a universe of galaxies, and that those galaxies are all receding from us due to cosmic expansion. The theoretical basis for cosmology starts with general relativity, our theory to describe expanding and curved space-time. And the Big Bang theory originates in the 1940s and 1950s. Modern cosmology, in terms of deeper understanding of the Big Bang model, is about 50 or 60 years old. There are ideas in cosmology that are simply assumptions. They're foundational premises that cannot be tested empirically. The most profound of these assumptions is called the Cosmological Principle, that the universe is the same in all directions and at all locations. There's even a version of this called the Perfect Cosmological Principle, where the universe is also the same at all times. That has now been disproven because cosmic evolution is a fact. Let's look at the two pieces of this assumption, isotropy and homogeneity. Homogeneous means that on average, the universe is the same at any location. This cannot be verified directly because we can't transplant ourselves to a different location in space. All we can do is use surveys to say that the galaxies we see hundreds of millions of light years away look very similar to the Milky Way and its neighbor galaxies, and that the Milky Way doesn't occupy any particular position relative to its nearby galaxies in terms of density or distribution. Isotropy is that the universe looks the same in all directions. That's easier to test because we simply make deep surveys with telescopes in all directions they can point. And isotropy has been confirmed with a high degree of precision. When the Hubble Space Telescope or any large telescope counts galaxies in any direction, the numbers are statistically the same, and the properties and behaviors of the galaxies are the same in any direction we look. Isotropy and homogeneity are foundational principles for understanding the expanding universe. Why is homogeneity impossible to test? It's because of the idea of look-back time. If we wanted to show that a distant region of the universe is the same as our region, we can't do it even in principle, because the light we gather from that distant region is seeing that space as it was long ago, not as it is now. We're comparing apples and oranges, or rather ancient apples to modern apples. So homogeneity remains an assumption as cosmology, although there's no reason to believe that it's not valid. There's an even deeper assumption that's also very hard to test, which is that the laws of physics are unchanging over space and time. We measure the laws of physics typically in the laboratory or in accelerators. These are terrestrial tests of something we assume to be universal. That's an enormous level of induction, and it may not be valid. What if the laws of physics change with time? What if they're different in different regions of the universe? This is an assumption that we need to test, however difficult it is. Hubble was well aware of this assumption when he measured the distance to Andromeda and showed that it was a separate system of stars. He recognized that he was assuming that Cepheid variables far away in space work just the same as Cepheid variables nearby in the Milky Way. He called this assumption the uniformity of nature, and he was a good enough scientist to put that as a caveat on his conclusion about the distance to Andromeda. There are some assumptions that are so profound they're almost implicit and rarely stated. For example, the assumption of causality. Science simply couldn't operate the way we understand it if events didn't have causes that we could identify. If events preceded causes, the universe would make no sense. Everyday life would make no sense either. But causality is something that doesn't have to be true in a hypothetical universe. It just seems to be true in this universe. It is indeed an assumption. We also, therefore, assume that causality holds in other remote regions of time and space. As an example of the importance of laws of physics being invariant, and the difficulty of testing them, consider nuclear physics. We routinely observe radioactive isotopes in faraway stars and even in faraway galaxies. We observe chemical elements throughout the periodic table at distances of 10 or 11 billion light years. We assume that these atoms and their nuclear properties are identical in far-off regions of time and space as they are in the terrestrial laboratory. This is very hard to test. Nonetheless, the stakes are so high with this assumption that cosmologists and astrophysicists and lab physicists have tried to make tests. One set of tests involves the fine structure constant, a pure number in physics, about 1 divided by 137, which accounts for radioactive decay. We assume that radioactive decay operates the same in our galaxy as in other galaxies. Clever astrophysical experiments seek to look for variations in the fine structure constant across large sections of the universe by watching spectral transitions in the gas far away and comparing it to gas in the lab. There have even been occasional claims that the fine structure constant does vary with time or evolves. These are controversial and have not yet been confirmed, but people are highly motivated to continue these experiments and indeed expand them. For instance, does the speed of light change over time and space? Does the gravitational constant change, or Planck's constant? At the moment, we simply don't know, so it remains an assumption that these so-called universal constants are indeed universal constants. To summarize what we know about cosmology, we know that the galaxies are receding from us, with a redshift we interpret in terms of expanding space-time, the cosmological redshift. We also know we've detected a radiation signature of an early hot, dense phase of the universe called the Big Bang. This radiation is isotropic, or the same in its intensity, everywhere in space to 1 part in 10 to the 5. It's incredibly smooth and uniform. Its temperature is just under 3 degrees Kelvin, corresponding to microwave emission. We also know that the hot, dense early phase of the universe created the light elements that we see, and their abundances measured around us form a test of the Big Bang model. Finally, with large telescopes, we get to observe galaxies at substantial look-back times, and we see that cosmic evolution has taken place. The clustering, the properties of individual galaxies, and even their numbers as they merge have changed over 12 billion years. In the modern view of cosmology, the two aspects of the universe that dominate the behavior of the universe are dark energy and dark matter. We have various ways of diagnosing them, using microwave observations, large clusters of galaxies, and very subtle signals in the galaxy distribution. These various measurements all seem to agree or converge on a model where dark energy is about 2/3 of the universe and dark matter is about 1/3 of the universe, and normal matter is essentially negligible. The microwaves themselves give us an indication of the curvature of space-time, which turns out to be very small. Space is flat to within 1% or so. And these observations also combine to agree that the universe is likely to expand forever at an ever-accelerating rate due to dark energy. The fly in the ointment on this large level of agreement is our fundamental uncertainty as to the physical nature of those two big ingredients, dark matter and dark energy. Modern cosmology is about 100 years old. Cosmology rests on some assumptions that are difficult to test. Primarily the cosmological principle, which says that the universe is homogeneous, the same in all locations, and isotropic, the same in all directions. The second of these assumptions has been well tested, but the first is hard to test because when we look at distant regions of the universe, we're looking back in time to an earlier state. Cosmology is based on the Big Bang model, and our evidence that the universe had a hot, dense early state is based on the expanding universe of galaxies and their cosmological redshift, the microwaves we see left behind from that hot, dense early state, the prediction of the light element abundance, matching parameters of the Big Bang model, and the fact that galaxies are seen to evolve or change in their properties over cosmic time.